Let's consider a heat pump that's going to be used to warm a home. This home will be the high temperature surroundings in the problem, 21 degrees centigrade. And we're going to have a lower temperature of the surroundings of the outside as 8 degrees centigrade. And so in between these two, we'd really like to have a heat pump. So what does the heat pump do? It basically pumps heat from the cold area into the hot area. And how does it do that? It takes in work. So we have to put some work into this situation to make this happen. The work obviously must go in, so it's less than 0. And really the way this heat pump is going to work is that it's going to basically be separated into two parts. Let's call them part A and part B. So the work in is going to allow for part A to become cold. Why would we want that? And let's go ahead and say that the temperature of A is going to be minus 10 degrees centigrade. What that would allow for is heat to naturally flow from the higher outdoor temperature of 8 degrees to the lower element A, or part A, temperature of minus 10 degrees centigrade. And similarly, part B now is going to be at a high temperature, 50 degrees centigrade. And that's going to allow for heat to flow naturally from this hot element B to the colder temperature inside the house of 21 degrees centigrade. We're asked to find the entropy generation. So the first law, d E dt equals q dot minus w dot. This is the first law. It's appropriate for closed systems, of which my heat pump is, right? It's not a blob, but it is a closed system. There's no mass going in or out. The second law, ds dt, is equal to q dot over ts plus sigma dot, where sigma dot is greater than or equal to 0. The problem is that we have more than one part in this problem. In order to do this in kind of a little bit more of a systematic approach, let's consider the differential form. ds is greater than or equal to ds on t. This is true. Let's consider that we have two different parts, a part A and a part B, and each one of them is going to experience an entropy change, and each one of them is going to experience a heat transfer. For part A, we'd have that ds of A is greater than or equal to dq over ts of A. Part B here, so if I were to add these two up, total entropy, right, dSA plus dSB greater than or equal to dq on ts of A plus dq on ts of B. Note here, this equation relates the system to heat transfer with the surroundings. So this equation right here is relating entropy change of the system to heat transfer and temperature of the surroundings. So what that would mean is that since the system here contains both part A and part B, it's a composite system, we don't include any kind of heat transfer in between these two parts, obviously. We only have to talk about the heat transfer between the system and its surrounding, not between parts of the system. So this dq is just the heat transfer of a part with the surroundings that is in contact with that part. So if we divide this through by dt and we rewrite in terms of entropy generation, we're going to have ds dt is equal to q dot over ts of A plus q dot over ts of B plus sigma dot, where we know, again, sigma dot has to be greater than or equal to 0. We start off here, but we've kind of moved to a second law that we can use for this particular problem that has more than one part. We're told for this heat pump that it has a coefficient of performance of 4. Assume that things are running at steady state. Why would we do that? We're basically assuming that if we take a picture of this situation, it doesn't change with time. That makes sense. It means that we've just ramped up to our stable operating condition. So whenever we have steady state, all of our time derivatives go to 0, and so we end up with some simplified equations that W dot equals Q dot in this case, and we also know that Q dot is the total heat transfer, which between the system and the surroundings, which in this case would be Q dot A. This is Q dot A. And Q dot B. This is the first law. All right, this is just rewriting this guy. The second law is going to look kind of similar. We're going to have that sigma dot is equal to a minus Q dot over Ts of A plus Q dot over Ts of B. We also know that Ts for A, the surroundings of A, is TL. Just like the surroundings of B are TH. Of course, B is not a surroundings of A. Why? Because the system is A plus B, just like A is not a surroundings of B. Why? Because the system is both these parts together. Lastly, that our coefficient of performance for a heat pump is the heat out. In this case, heat out is going to be Q dot B. That's the heat out of the heat pump over the work that I'm putting into this thing. This is 4 in our case. In other words, Q dot B equals 4 times W dot. Plugging that into here and subtracting over, we would have that Q dot A is just going to be equal to W dot minus Q dot B, which is going to be minus 3 W dot. Of course, in this case, I know that W dot is actually less than 0. So this is a negative number. Q dot B is negative. Heat transfer out is negative. Whereas this is negative of this is positive. Why? Because heat transfer in is positive. So sigma dot is going to be equal to a minus. Q dot A is a minus 3 W dot over TL plus Q dot B is 4 W dot over TH. It might be helpful here actually to factor out a W dot. For this particular problem, we have W dot is minus 10 kilowatts. Minus 3 is a pure number over TL. TL is 8 plus 273.15 Kelvin plus 4 over TH is 21 plus 273.15 Kelvin. 29.2 watts per Kelvin is the entropy generation I have in this problem. Lastly, just as a quick aside, we could actually also consider the entropy generation not just of the entire system, but of each individual part. So we could consider the entropy generation of just Q dot A going from the low outside temperature into the even lower element A, or part A of the heat pump. And we could also consider the entropy generation due to heat transfer from B into the house. So we could talk about those smaller constitutive entropy generations as well.